Hello everybody, I am Sarp Yılmaz, a student at Bilkent University. My department is mechanical engineering. In this video, I'll be talking about and presenting my experiment. First of all, I'm going to talk about what I did in the experiment. My experiment consisted of two parts. In the first part of the experiment, I wanted to measure the magnetic field inside of a couple of solenoids. And in the second part of the experiment, I wanted to measure and investigate the drop-off rate of the magnetic field strength created by a solenoid according to the distance. Now, let me briefly touch on the theory of the experiment. Solenoids are a type of electromagnet which are created by making multiple turns of a conducting wire. This wire is later provided with a current, and as a result, the solenoid creates magnetic field inside of the solenoid. Now, there's a formula which is shown on screen to find the strength of this magnetic field. Normally, this formula applies to perfect infinite length solenoids. However, in real life, when the length of the solenoid is much bigger than the radius of the loops, the same formula can be used to find the magnetic field in the center of the solenoid as well. In the first part of the experiment, this formula was used to measure the theoretical values and compare them to the real life measurements. In the second part of the experiment, I want to see how magnetic field changed according to the distance. Normally, a magnetic dipole's magnetic field is calculated using the formula given on screen. This formula can be further simplified when the measurements are done on the same axis as the polar sides. As you can see, the simpler equation is inversely proportional to the cube of the distance. Since solenoids have polar sides such as north and south as well, it was originally assumed that the magnetic field created by these solenoids would act similarly as well. So it was assumed that the magnetic field created by a solenoid would be inversely proportional to the cube of the distance. Now, in the first part of the experiment, I used three different solenoids. I used a PVC and cardboard as the base. I tried to keep some of the values same while making these solenoids. For example, for two of them, the amount of turns is the same, but the length is different. And for other two, I kept the length the same, but the amount of turns is different. I basically tried to make it so that only one variable was different between the pairs. This way, I thought that it would be easier for me to see how the distance or amount of turns affected the magnetic field separately. I was basically forced to keep the current same for all of them because I decided against using resistors during the first part of the experiment, and without resistors, at max I was able to provide them with 0.8 amps. The measurements were done with a Gauss meter. The instrument was unreliable at first. However, eventually I was able to get some steady readings. The readings were compared to the theoretical values, and the errors were calculated. The errors were not very low, but were not very high either. Especially the second solenoid's error rate was quite low. In the second part of the experiment, I used a different solenoid. Since the magnetic field is directly proportional to the permeability, I decided to use a ferromagnetic base to increase this permeability. If I didn't, the values would be extremely low. In fact, so low that my phone's Hall effect sensor wouldn't even detect it. I had to use my phone's Hall effect sensor for this part because by the time I was doing this part of the experiment, the Gauss meter had stopped working. For this part of the experiment, I didn't focus on any theoretical values. I only looked at how the magnetic field dropped according to the distance. I measured the magnetic field from 5 different points along the axis of the poles, and I put them on a graph of 1 over the cube of the distance versus magnetic field strength. Since we assume that magnetic field is inversely related with the cube of the distance, magnetic field should be directly proportional to 1 over the cube of the distance. The graph is consistent with this assumption as well, so we might be able to say that magnetic field created by a solenoid is inversely related with the cube of the distance.